Let's begin this. So chapter 5 is more about exponents in the beginning. We're going to kind of jump around. This is our last section before the midterm. So you've done everything already to the midterm at this point. This is the last one. And then after the midterm, we'll come back. We'll do section 5.3 and 5.4. And then we're actually going to jump right to chapter 6. We'll come back and finish chapter 5 at the end of the year, and I'll explain why that is later. So for today, we have to remember is these are more rules of exponents. Okay, now, the first 4 rules I want to talk about, we covered them already in section 4.2. So in sections 5.1 and 5.2, they reiterate all these rules. 4 of them, numbers 1, 2, 3, and 4, we already covered. Okay, we already covered these. So let's quickly look at them. What does the first rule tell me? Give me in your own words. In your own words, please. Rule number 1. How would you make a statement? I want a full statement as to how this would work. Go ahead.
When you multiply numbers that have exponents in the same base, you just add the exponents.
Very good. If the bases are the same and you're multiplying things, you add the exponents. Why is that? Here it is, right here. Everybody look down. I know it looks annoying. You would never do this, right? Would you honestly ever write this out? No. But you want to see why this is true, that you add them? This is why. Y to the third, y to the fifth. 3 and 5 is 8. Well, look. 3 y's there, 5 y's there, a total of 8 y's. Because multiplication is commutative. Okay? That's why you're allowed to do that. 0 exponent rule simply tells me
anything to the power of 0 is 1.
Anything to the power of 0 is indeed 1. The simple conjecture for this is to look at powers of 2. 2 to the second is 4. 2 to the first is 2. Well, what is 2 to the 0? What's happening? These are halving every time. So it's always going to be 1. You can do it with any number and it will always prove it true.
But the halving thing is only for 2. The halving thing is only for 2.
Yes. So if you tried the number 7 or the number 3, 3 to the fourth is 81. 3 to the third is 27. 3 to the second is 9. Those are going down by thirds. Yeah. Halving for 2, thirds for 3, fourths for 4, etc., etc. Number 3, power to a power. What do you do? Tell me, yeah.
You multiply the powers.
That's it. A power to a power tells me to multiply the powers. If you don't remember these rules, you will be at a detriment because you're going to be slower on the test. But if you for some reason forget, at least remember you can prove it to yourself. What is x to the third to the fourth really mean? It means x to the third, x to the third, x to the third, x to the third. And then you can use rule number 1. 3 plus 3 plus 3 plus 3 gives you 12. So if you forgot to multiply these, that's how you can always check. When I was a student, I was not a good memorizer. I hated biology because I couldn't memorize. I loved chemistry, I loved physics, I loved math. But certain parts of math I had trouble with memorization. This was one of those. So I sometimes didn't really even remember the rules. I would quickly prove it to myself on the side. I'd say, wait, what does this mean again? Is it product? Okay, there it is. And I'd literally just write these like 3 or 4 things out real quick. Okay? But it saves you time by memorizing them. That's why you want to memorize.
If 2 powers are divided, then subtract, right?
Yes, and actually, you're jumping the gun. That's number 5. We're going to get to that in a minute. Yep. A power of a product. What is that really saying to do? A power of a product. What are we doing?
Each variable, you raise it by the exponent.
Good. You raise each of the factors in here, in the product, to that power. It's like distributive, but I don't want to call it distributive. You see what I'm saying there? Do you see how it's like distributive? You're technically like distributing the seed of both of these, but I don't call it distributive because it's not. Distributive involves addition. Okay? So a power of a product, take each of those factors. What if I had like 5 factors? Same thing. Proof of it is right here. Very simple. 4 times 2 to the third. What's 4 times 2? 8. 8 to the third, 5, 12. There's your answer. But if I wanted to prove it with the rule, 4 times 2 to the third is 4 to the third, 2 to the third. 4 to the third is 64, 2 to the third is 8, 64 times 8 is 512. Same answer in both cases. Okay? Yes, no, maybe so? These should all be things in the back of your mind from already having learned. Even these you might have already learned, and this is the one that Tristan was just talking about. Now, let me point something out. Yes, the rule is absolutely 100% subtraction, right? The rule is indeed subtraction, for sure. But if you forget, prove it to yourself. Look at the example. Ready? X to the fifth over x to the second. Oh, I forgot. Is it subtraction? What is it? I don't know. So think in your mind, what does x to the fifth really mean? What does x to the second really mean? What do I know? I know that if I have factors in the bottom and the same factors up top, what happens to them? They cancel. So cancel 2 of these with 2 of these. How many are you left with? Therefore, 5 minus 2 gives me 3. There's your simple proof of this rule. Do you see the simplicity of this rule? How easy it is? Let me give you a complicated example. Try this one on your own to see if you get it. Let's say the following. H cubed n all to the 4th over h squared n to the 3rd. I don't know why I used h and n. That was stupid. They look the same. H cubed n all to the 4th over h squared n all to the 3rd. Go about simplifying this, and please be careful. PEMDAS. PEMDAS. Think about what you have to do. I'll give you about a 30-second head start, then I'm going to put the answer up. And I want you to tell me what the common mistake would be in this also. Did you all get h to the 6th n? H to the 6th n? If not, take a look up and see where you made your mistake. It's really a power to a power, isn't it? And it's distributing that power at the same time. So you are using 3 rules here at once. It's a power to a power, which means multiply. There's a product inside of here with a power, which means you have to kind of like distribute that. And then the quotient rule afterward. What's the common mistake here? George, what's the common mistake you think?
Probably to add the exponents and distribute.
Maybe. That's one of them, for sure. I could see that. George makes sense. Maybe people write h third, h4 as h to the 7th. I could see that. That's one common mistake. Give me another.
Like you divide into these things instead of subtracting.
Okay, so maybe you take 12 and divide by 6 and put a 2 here. And this, people put a 4 over 3 and put 4/3. That's another. These are great. 2 mistakes right there. Give me another. I can think of 2 more.
Just subtracting without simplifying.
Yeah, so it's taking 4 minus 3 maybe, making that a 1. Or even taking 3 minus 2 and 1 minus 1 and saying, oh, these cancel because it's n and n. They cancel, right? Not because these are here, they don't cancel. Okay? There are many ways to make careless mistakes here. So you need to be confident in your rules. Okay? You have to understand them like the back of your hand. You know what that saying means, right? Like the back of your hand? Because you see the back of your hand all the time, you should know what the back of your hand looks like. I like to know etymology. Anybody else like that or no? I love to know etymologies of sayings. I don't know why. How about this one? Happy as a clam. Why does that make sense? Most people think one thing and it's not actually it. You're going to probably say what?
I'm probably going to be wrong, but because clams, they're always opening their mouths all the
Yeah,
time.
people think it's like a mouth or smiley and stuff. It's not.
Or a pearl because, it's
Okay, I can see that too. You know it?
Because when people caught the clams, they would be happy.
No, they get eaten if they're getting caught. It's the opposite. The whole saying is actually happy as a clam at high tide. Nobody ever says the last part. Why would a clam be happy at high tide? Who knows that? What does high tide mean?
Because then the water's like all the way up here.
And the clam is where?
He's like there.
Yeah, it's under the water. It's safe. It's happy. When there's low tide, what happens? All the clams are exposed. That's when people go clamming, they wear these little clamming. Ever gone clamming before or no?
Yeah.
You just walk in the water and they just like grab onto the bottom of your thing. Right? Isn't that how it works?
Yeah.
I've never done it.
Yeah. I went from like Rhode Island with like when I went there with friends. And I was like 6 and I dropped a whole bag of clams.
Oh, they probably yelled at you
Yeah.
because they all got free, right?
Yeah. But
Well,
then we got
I'm sure you picked them back up, actually, yeah. But when the tide is low, the clams are exposed. That's why it's happy as a clam at high tide. Anyway, there's a lot of sayings. You should look up sayings. It's kind of interesting. Because people use them all the time, but they have no idea what they actually mean. All right, so how about I pose this question to you? What happens when the degree of the numerator is less than the degree of the denominator? And look at the example. M to the 4th over M to the 6th. Well, using Rule 5, this is what we get, isn't it? If I have m to the 4th or m to the 6th, what do? It's a quotient. A quotient tells me to subtract the exponents. So if I subtract 4 minus 6, I get negative 2. So that's the answer. But look, if I use the cancellation rule instead, look at the cancellation. I've got m over m. Right? Looks like a lot of right? Are you getting hungry here? So 4 of these m's cancel with 4 of these m's. When 4 of them cancel with 4, it leaves you with 2 in the bottom. Right here, it leaves you with those 2 in the bottom. But remember, when you cancel things, you have to put a 1 left behind. So the numerator has a 1 in it. The denominator has a 1 times m times m. So a 1 times m is this. That's m squared. And the numerator is a 1. So how does this help us with the next rule? You could look ahead if you want to, or you can try and come up with the next rule then. How does it help us?
Helps us find negative powers.
Yes, it defines a negative power. So look, if these two things, look what I'm circling, please. If those two things are the result of the same operation, they must be equal to each other, right? Agreed? If I take m to the 4th or m to the 6th twice and do it differently but get 2 answers, those answers have to be the same. So what this says is that this is really this. Use that to understand rule number 5. Okay, use this to, number 6. Use this to understand rule number 6. So let's press on to rule number 6 so we can see that. So rule number 6 tells me what? When you have a negative exponent, what should you do? What should you do?
Make the exponent positive and then put 1 over it?
Yeah, and put it in the denominator. Good. What if the exponent is negative in the denominator? What do you think will happen? Come on, use your intuition.
Then it'll be like a positive?
Where though? If it started in the denominator, I'm leading you, I'm prompting you. It starts in the denominator, where could it only go?
The numerator?
The numerator. Think about that. So if a to the b is 1 over a to the, if a to the negative b is 1 over a to the b, you could also say this. Okay? Again, if you have a negative in the denominator, move it to the numerator. So let's write this down. Write a little note, put a little asterisk. Whenever you have a negative exponent, make it positive and move it from the numerator to denominator or denominator to numerator. You could say change its position in the fraction also, if you want. Again, simply make it positive and move it from the top to bottom or bottom to top.
So
Yeah.
you just say that you basically, in order to get it to be positive, you just make it reciprocal.
Sure. Yep. Absolutely. And that's what this is. This is a reciprocal law here. A to the negative b equals the reciprocal of a to the b, which is 1 over a to the b there. So again, make it positive and move it. Hey, look at the second one. Can somebody explain the second one to us? How come a over b all to the negative c is really b over a all to the positive c? Explain the second rule. Ash, go ahead.
It's like you make a to the c, but you have to like flip it to this number, so it becomes if a moves to the number, and for the b it's like b to the c, but you have to move it to the numerator. So if you put it together, it's b over a to the c.
Yeah, that's exactly right. So what she's saying is this. Look, this is really this. Right? By your rule of something to a power, wouldn't they both be to the negative c then really there? Isn't that what's happening? Now, as a result, if that's the case, actually we didn't even do that rule yet. That's rule 7, sorry. I'm kind of jumping the gun by showing this explanation. But rule 7 tells us if we have a power outside of a quotient, both parts of the quotient get that power. Well now, rule 6 told us with a negative exponent, switch the spot. So a to the negative c goes to the denominator as a positive. b to the negative c bumps up to the numerator as a positive, and then this goes back to that. Follow the arrows, please, to see the proof. Starting with what you have, a over b to the negative c, that's really this. When these are negative, it means move it to the bottom, make it positive. Move it to the numerator, make it positive. And then what is this really, though? B to the c over a to the c is really b over a to the c. I promise you, it seems like these are just annoying rules. You will use them with some mathematical context. You will use them a lot with what are called logarithms next year. Okay, in your geometry course at the end of the year, fourth quarter, you do a little bit of algebra actually in your geometry course next year, and you're going to cover what are called logarithms, and you'll see where this rule gets applied. Okay? It's hard to show where it's applied without going into logs, and I can't just go into logs. It's a whole new topic to end and teach. Some of you might know about what logarithms are. If you do, you'll see where these rules come into play with logarithms also. They come into play with power functions, exponential functions, different things that you're going to learn about, also in pre-calculus in your junior year. All right, let's go on. Let's do an example before we go on to the next one. So let's try this one, please. So let's take a look at this example, and the question says, simplify and give your answer with all positive exponents. Simplify and give an answer with all positive exponents. Give you a head start, 30 seconds again. Is today exam? It is, right?
Yeah.
Thursday? Oh, we got a lot of time. Never mind. What do you notice about this problem here? What do you notice right away? If you were to use your division rule and just subtract the exponents, if you take a look at the x part, what's x to the third over x to the seventh going to give you if you just subtract them? 3 minus 7 is what?
X to the negative 4.
It'll be x to the negative fourth, wouldn't it? And if that's in the numerator, what are you going to have to do to it?
Put it in the denominator.
As x to the positive fourth. So here's how I interpret this problem. Let me give you a little tidbit of help. When you have a fraction, just think about cancellations. I would not do 3 minus 7. Here's what I would do. I would say, okay, 3 of these cancel with 3 of these, leaving 4 behind in the denominator. That's how I would start the problem. It doesn't make sense to do subtraction, get a negative exponent, and then make that negative exponent positive by moving it. I would literally do that to start. I would say 3 of the x's up top cancel with 3 of the x's on the bottom, leaving out of the 7 in the bottom, 4. Does that make sense what I'm saying? Because if you did it the other way, you would have 3 minus 7, and your answer would be, okay, x to the negative 4 up here, which would then move to the bottom as x to the positive 4 anyway. So I prefer to cancellation when it comes to a fraction. How about the y part? Y squared over y just becomes y. Cancel that, 2, with this whole thing. So now I'm at the point where I've got a y here over x to the fourth, or I could look at it over here. This way, if I did it that way, it would look like that. And then over z to the third. Z to the negative third, sorry. So if z is negative, the exponent is negative rather, where does it go? It goes up top as a positive. Okay, so here's your answer at the bottom. You could have taken the step with subtraction, you would have that, and then you'd have to move x to the negative 4 down to the bottom. Hey, what if I had numbers in front? What if I had something like this? Because this is a mistake I see all the time. How about this? What if I had... What does that simplify to? And again, please, don't use the division rule. Don't say negative 4 minus 3. You're going to get negative 7, then you got to move it down. Just think about the x to the negative 4 and what you should do with that to start. What does this answer become? What do you start by moving right off the bat? What do you do? Okay, so you can make this 1/4 to start, right? Like that. I agree. That works. Yeah? Thank you. And then what do I do with that? Bring it down. Okay, so the answer would become 1/4x to the 7th. The common mistake that I see a lot, and I want to make sure you understand that it's not correct, is students move the x to the negative 4 to the bottom in the beginning, and they also move the 2 down with it. Again, look at the 2. The 2 is a coefficient of x to the negative 4. 2 is not raised to the negative 4th power. It's not 2 to the negative 4, right? The x is to the negative 4. But what if I had done this? If the problem changes to this now, and it's the quantity 2x to the negative 4, that entire quantity gets moved down. You see this? Okay, the entire quantity will move down now. But it's not the case that we have. We happen to have this case right here. So remember that the exponent is attached to the variable, not the number that's the coefficient in front. Yeah? Okay. You're a glazed look on your face for a second. I wasn't sure if that was a question or you're just relaxing. Last rule is the one that we kind of talked about already, right? In the last one just now. So if you have a power of a quotient, you distribute it similarly. The word is not really distribute, but you expand it to both. You apply that power to both terms. So let's look at an example of this. X to the 3rd, y squared over x squared, y to the negative 4, all to the negative 3rd. There are 3 ways to start this problem. Let's solve this in all 3 ways. You get the same answer in all 3 answers, but there are 3 ways I can think of to start this problem. Give me one way to start it, please. We'll take 3 roots. Let me mix this a little smaller so you can see. We'll do it 3 different ways. What's one way to start this problem? What's one way to start it? George, go ahead. Yeah, raise everything to the negative 3rd, which would give me x to the negative 9, y to the negative 6 over x to the negative 6, y to the positive 12. That's one way to start it. Apply the exponent. That's the first way. Yeah, it works, right, George? That works, but now I got to move a lot of stuff, don't I?
Yeah.
It's a bit messy. Give me another way to start the problem.
You could
Simplify within. Absolutely. Simplify within. Which tells me that, okay, x to the 3rd over x squared just gives me x. Y to the 2nd over y to the 4th is y to the 6th. And then I can go about distributing my exponent. Agreed? Simplify within. That works. What else? What else? One other way to do it. One more way. Come on. Who can see it? Let's go. Let's go. Come on. Who can do it? There's a 3rd way to do this. I want you to think of alternate ways. Okay, so what would it look like?
It will be x squared, y 6.
X squared. You're on the right track. I would definitely make that a positive and switch it. But I would go like this if I were to do it the 3rd way. So this is flip the fraction and make the exponent positive. It also works. It's completely right. You can definitely do that. Remember the example, if you look back at your rules, one of your rules told you if you have a negative exponent outside of a fraction, you can just flip the fraction and make it positive, right? Because the negative exponent means aren't these all going to be flipped anyway? Yeah, that's what's going to happen.
So you know like how it will be x squared, x cubed, y 6 over x squared.
Well, we haven't solved them yet, so we have to keep going for all of them, right? And continue.
Like we need x to the 4th power up. Oh, y.
Bring the y to the 4th power up. Okay, we did that here, I think, though, right? We brought the y to the 4th power up here, and we simplified the x here. That was simplifying within. This was the one that most students wouldn't probably necessarily do right away, and I agree that this is probably the lengthiest. I would have chose root 2 in blue. I think blue is the fastest answer, right? This would give me, which is really that. In black, I would get this. Well, see, here's the thing. The one that's in black, now we could actually do it two ways also. That could branch out into two options as well. Let's do the one in red next. In red, we've got x to the negative 9, x to the negative 6. We've got to move all this stuff. I switched my variables in the blue. Anybody see that? You saw that, Max? Good eyes, Max. Y to the 18. I switched the x and y in the blue by accident, sorry. Okay, look in red and blue, you get the same answer either way. Whether you apply the exponents first, then switch all the negatives, then x to the 6, x to the 9th becomes x to the 3rd, right? Y12, y6 is y to the 18 here. These guys cancel, giving you that. This answer is the same as this answer. In black now, over here on the far right, we could actually now apply the 3 to everything, or we could simplify within first. 6 1/2 dozen, right? It doesn't matter which way you go. Anybody know that one? 6 1/2 dozen? What does that mean? 6 1/2 dozen. When somebody says that to me, 6 1/2 dozen. What are they saying? Doesn't matter either way. What's a half a dozen? 6. It's just a saying. 6 1/2 dozen. I didn't get that one when I was a kid, actually. I remember. All right, 6 1/2 dozen. Whatever. It's the same method whether you choose either direction. So in this case, in the third, honestly, you could choose any way to do it now. You could simplify within first, which would make this an x left in the bottom, and y to the 6th in the bottom, and 1 up top, and leaving the 3, which still becomes the same answer. Or if you really wanted to go crazy, you could have done it like this. You could have said, let me distribute the 3 first. Makes that a 6. Makes that a negative 12. Makes that a 9. Makes that a 6. And this then becomes the same answer again. Okay, again, what am I doing? I'm becoming annoying, I know, at this point, right? It's redundant. You can do this problem in so many different ways, it doesn't matter. All right? So it's up to you to take that approach. But remember, you can't take any approach. Some approaches aren't correct. The approaches I just showed you are all acceptable for this kind of a problem. If you can do that last problem, that's kind of understanding all the rules in one, right? You're doing almost all the rules at once. All right, that's it. Homework from 5.1 and 5.2, and then some review questions. Real quick, we got 4 minutes. What were the questions from 4.8? Ash, you had one, and then Tristan.